Okay, today we are going to start on the dimensionless variables. So, if you remember the diffusivity equation, how many variables we have in this one? Okay, first we have pressure. Pressure is the dependent variable on what? The radius and the time. And what about the others? Porosity, viscosity, compressibility, and permeability. So we are solving the diffusivity equation for pressure. Okay? But when you solve it, you can solve for a certain value of permeability. Or you can solve for a value of porosity. So this doesn't make the equation general. So what we need to do, we need to come up with a form which has no units that makes the equation dimensionless. Okay? So we are solving the equation for P. And the pressure is a function of what? What? Okay, so the pressure is a function of time and radius. So we need to define first the dimensionless pressure, which is a function of dimensionless time and dimensionless radius. Okay? Okay, but before that, how do we do that? Do you have any idea how to define the dimensionless variables? Okay, so since there is no answer, this is the diffusivity equation in dimensionless form. And then if you look at the variables, RD and TD. So how do you define RD first? We have R, okay, in the equation. And RD must be something that should be related to R, and we should select a characteristic value, like RW. So this is by intuition, okay? So you take your RW, which is the valve radius, and then if you divide R parameter with RW, then you end up with R dimensionless radius. Okay? So as I told you, this is defined by intuition. The next step is to define the dimensionless pressure. So how do we do that? We do that by looking at the problem, and then we will define this by the conditions of the problem. Okay? But before going into that, so tell me, how do we solve this partial differential equation? What? Yeah, I mean. That's right. Okay, somebody says Laplace transform is right. Yeah, this is the first thing. You use Laplace transform to solve a differential equation, partial differential equation. But before that, you need something for the particular solution. First, you need what? Conditions. Yeah, conditions, but what conditions? How many boundary conditions? 3? Yeah, 2. And what are those? No, no. The boundary conditions are related to your position. So the first boundary condition is your inner boundary condition, okay? And the second boundary condition is the outer boundary condition. And there should be one initial condition. It is the value of the pressure at time equals 0. So it's going to be your initial condition. And initial condition will always be initial pressure. Okay? So we define our boundary conditions and initial condition. So now we are going to go and solve this partial differential equation. And the first, we can do that by what? Laplace transform? Okay. And what about other methods? Do you know how to take Laplace transform, by the way? Yeah, don't worry about it. We will not see this. Okay, the second method is the separation of variables, right? Methods of characteristics. These are the methods that lets you to solve differential equations, okay? And the third one, or another one, is solve a partial differential equation numerically, right? So if you solve this equation numerically, then you can write a reservoir simulator. So it is, if you look at the reservoir simulators, I mean, all of them are based on the solution of this equation. This is the building block, okay? And this equation has no units. So this is a general form. And then what you do, when you solve this, you insert the definitions of the dimensionless variables, and then you can understand what is your pressure at a certain permeability, at a certain porosity, or something like that. Okay, so as I said, we define our initial condition and the boundary conditions according to the problem. So the initial condition is always the initial pressure, right? But before going into that, there are 3 magic numbers in the universe, okay? So what are those? What? 5? Okay, 0, minus 1? No, 1, yes. And can't hear you. Infinity, you say? Okay. Okay, 0, 1, and infinity. And why are these our magical numbers? Because you obtain 0 by dividing 1 over infinity, right? Vice versa. And we use these for mathematical convenience, nothing else. Okay, so our first initial condition, I said initial pressure. So we define our dimensionless initial condition to give us 0. And you will see in the solution, this will make your life very easy. Okay, and inner boundary condition, we set it equal to minus 1. The reason for minus is you will see in the solution, it's also a mathematical convenience. Okay. So most of our solutions are based on constant flow rate inner boundary condition. So we impose a constant flow rate at the wellbore. So how can we do that? How can you obtain a constant flow rate at the wellbore? What equation you use for it? Okay, what is the equation for the flow rate? You remember? You derived it in some exercise problem. What? It's Darcy's law, right? So if you write Darcy's law, okay. Okay, what I did was I take the Darcy's law and then I define the R, dP dr term, and I set it equal to a constant. Okay, and then when you use the definitions for the dimensionless parameter, then this constant will equal to -1. Okay. Okay, so we use the Darcy's law. We set a constant flow rate at the wellbore, and this became our the inner boundary condition. And there is also another thing missing here. We are missing the outer boundary condition. Yeah. You mean why -1? Because in the solution you will see that. I mean, if you go ahead and solve this, you will see -1 will be very helpful, because if you use 1, then it will be more complicated. It's all defined by, mathematical convenience. Okay? So that's the reason. There is no physical theory behind it. You just define it to be -1. And the outer boundary condition will be first the infinite acting reservoir. So if you use the outer boundary condition PD, so this will depend on the value for RD. So if you impose an infinite boundary condition, then RD will go to infinity. And at infinity, your pressure will be the initial pressure. So you can impose your outer boundary condition to become 0 if you have a reservoir which is infinite acting. Okay? And there are several other boundary conditions, like you can impose a circular boundary reservoir or constant pressure reservoir, but we are not going to see those. We are going to see the infinite acting reservoir solution. Okay, so we have our initial condition and boundary conditions. Then we can solve the partial differential equation and obtain our dimensionless pressure. But before that, if you use the definitions, these will be your dimensionless pressure, time, and radius values. Okay? And this is defined, the dimensionless pressure, for the constant rate at the wellbore. Okay? So don't forget that. If you have constant flow rate at the wellbore, this will be your dimensionless pressure value. And this PDC is the unit conversion term. So if you are using Darcy units, which you are not going to use, it's equal to 2 pi. But if you are using field units, then which you are going to use it all the time, then it's equal to this number. Okay? Yeah.
But we don't always have the constant flow rate at the lower.
What can we have then? Okay, the question is, we don't have constant flow rate all the time at the wellbore. What are the other boundary conditions? You can keep the pressure constant at the wellbore, right? So you define another boundary condition then, okay? And as far as I remember, so if you use a constant pressure at the wellbore, then this will be your definition for the dimensionless pressure, which is P minus PWF, that is constant, over PI minus PWF. Okay? This will be your dimensionless pressure. Okay. But somebody tell me how you obtain this definition for PD. Because this is not based on intuition. We cannot say that PD is something similar to R over RW. Because you remember we set this RD by intuition. We say, okay, RD is equal to R over a characteristic value for radius. But for the case of pressure, we cannot do that. So tell me how we obtain the form of dimensionless pressure. What? Yeah, we use Darcy and yeah, that's actually you're on the right track. We use the initial condition and boundary conditions to define our dimensionless pressure. And the first inner boundary condition was Darcy's law, so we can use that. And also we can use the form, the initial pressure. We can say PD is equal to a characteristic pressure, but it should be multiplied by Pi minus P. So since if we impose PD to become 0, this then will be the correct form, right? Because PD equals 0 at the initial condition, so at the initial condition your P will become Pi. So this form will equal to 0, right? And then this was the first step. The next step is to solve for the P characteristic, and you do this by using the Darcy's law, as you said. Okay? So let's recap. The dimensionless pressure defined by the conditions you are imposing. It can be a constant flow rate at the wellbore, constant pressure at the wellbore, infinite acting reservoir or finite reservoir, or constant pressure at the outer boundary. So they will all change. But in this class, we will most see the constant flow rate at the wellbore and infinite acting reservoir. Okay?
So you said that the characteristic pressure is solved using the Darcy's law?
Yeah, you obtain it by using Darcy's law, but where do you use Darcy's law? You use Darcy's law at the wellbore, right? You are imposing a constant flow rate at the wellbore, so you take that and then force it in the PCH, the characteristic pressure, and then you obtain the value for PD. Yep. Yeah, you can assume constant. But your outer boundary condition will change. So you won't say PD equals 0. PD will equal to something else. Or what you can do, you can also impose the Darcy's law in the outer boundary as well, and define another form of dimensionless pressure. Okay? Okay, so what you are looking at right now, this is the solution of the dimensionless diffusivity equation. Okay? So, do you know what E1 is? E1 is called the exponential integral. So it's a mathematical function, and we will see that on the next slide. But how do we obtain this solution? We go back to the diffusivity equation and use Boltzmann transform, and then it becomes an ordinary differential equation, and then you can solve the ordinary differential equation easily and then plug back these values and obtain this form. And also we made another assumption. This is called the line source solution. So actually this is supposed to be your well, but here you assume a line, not a cylinder. So if you assume a cylinder, then you won't get this solution. It will be much more complicated. But if you assume a line source like this, then this will be your solution. Okay, do you remember the definition of the well testing derivative? What if you take the derivative of this equation? Okay, what was the well testing derivative? So this was the definition of the well testing derivative. And if you take this solution and the derivative of it, then you will end up with this. So 1 over 2 exponential something. Okay? This is actually a function, but here you can assume something. Let's look at the values for TD. Okay? So if TD goes to infinity, what happens? What? Okay, just imagine an exponential function. An exponential function always increases, right? But we have the minus sign now, so it will decrease. Okay? And we have the TD in the denominator. So if TD is high, then the value for the exponential function will be very low, right? So if it keeps going high, then the well testing derivative function will eventually equal to 1 over 2. So this tells you something. This tells you that the well testing derivative will always become 1 over 2 at large times. Okay? Sorry, but for large values for TD. And then when you convert TD back into the dimensional form, then you will see that this will happen for most of the time. So when you will look at the pressure buildup data or some other buildup data cases, you will see that the derivative, if the derivative is equal to 1 over 2, then you see the infinite acting radial flow. That's the solution. So as I told you, this is the exponential integral function. And it's tedious to compute this function, and you have to write a program to compute the values for the exponential integral. But you can expand this exponential integral in series form. So if you expand this, then you can approximate the solution, and the solution can become 1 over 2 ln something, okay? So this is valid for the values of TD over RD squared higher than 25. So this is basically a good approximation. And then if you take the derivative of this, then you will see that the value testing derivative will equal to 1 over 2. So how do we do that? Here is your exponential integral, and you see that it's not easy, but this is the series expansion for the exponential integral. So you omit this term, and then you see that it is basically and then if you go ahead okay, so you can do this. This is basically the equation that I showed on the previous slide. So this is a way to approximate the exponential integral. And then if you do this, and then plot your results, okay, now what you are looking at is the blue line is your log approximation to the derivative, so it's always constant. And the red line is the exact solution of the exponential integral. So the difference is only up to TD equals to 1, okay? So if you remember the definition of TD, okay, so this is valid for values TD over 1, but TD, if TD is less than 1, then you see this difference, but if you set this equal to 1, the T values, if you go ahead and compute the T values when TD equals 1, you will see that the T values will be so small, okay? So we are lucky that this is so small, so we can use the approximation all the time, okay? Sorry? No, the solution is defined in terms of dimensionless time, okay? And you see that the difference is, you see the differences for values less than 1. So now I am trying to find the value when TD is equal to 1, okay? And when TD equals to 1, the T will be very small, so you can use the log approximation, okay? And this is another way to look at the solution. This is a cylindrical source. This is the line source solution, and this is your log approximation, okay? So you see the differences for TD less than 3, and when you compute the T from TD less than 3, you will see that T will be very small as well. So this tells you that the logarithmic approximation for the pressure solution is a good approximation, and you use that for all cases in future, okay? Okay, is there any question?